All right, so this last section is just kind of trying to hammer away at this idea that if you have paired data, you need to run a match pairs test, okay? Students often get these two procedures mixed up, and the reason is pretty obvious. I mean, if I take a look at this thing, I got, you got two lists of, or I should go back to this one up here, or whichever one it is here, this one here. I got two lists of data. It looks like two samples. We got a regular lane and an express lane. I put those two things in my calculator. I run a two sample t-test on the difference of whatever, and I put in the two lists, okay? So, and if you do that, if you make that mistake on the AP test, you're gonna lose a lot of points. Like, this isn't just a minor, like, oh, maybe one, like on my test, you'll probably lose probably 9, well, it's not gonna be, well, you lose a lot of points. On the AP test, you'd probably drop from a 4 to maybe like a 1. Because it's just completely the wrong procedure, and it's hard to award partial credit for it. So it's very important to understand which of these tests we're supposed to run, okay? It's easy to determine if you look at the design of the study. It's hard to determine if you just look at the data, okay? So read the question and put some thought into it. A paired t-test is used on a match pairs design where our data is linked. Each data point is on one set is linked to the other set, okay? And you do a two sample test if you have two independent samples, okay? So let's just determine which test we would run in this situation. You're wondering if the men at the John Cooper School are taller than women. So you select a simple random sample of 30 girls, and you select a simple random sample of 30 boys. Which inference procedure should you run? So again, if you just look at this, if you just look at the data and the graphs, there's no way to know. You have to read the text to see that we got two different independent samples. Therefore, we should be doing a two sample oh, my dog is eating my cord. What? Oh, stupid dog. T-test on mu1 minus mu2. I got two different means, and I'm wondering if there's a difference in the means. These are two independent samples. That is why I run a two sample t-test, okay? So we got males and females, the distributions are different, we run our test, yada, yada, yada. It's all pretty standard. We'll talk about this a little bit more, but we do need to get a little bit more used to looking at computer output. So this will kind of be the focus when we start doing a little bit more review for the AP test. It's very rare that on the AP test they have you actually type data into your calculator and run the test yourself. They'll just kind of give you computer output, and you have to interpret the computer output. This is from Minitab, a software program that, I don't know, it's pretty commonly used in industry. So it looks like we got a two sample t-test for males versus females. Here's our summary statistics. We got the mean, standard deviation, sample size. This is the standard error of the mean. This is the standard error of x bar, which is s over square root of n. So if you were to take 69.06 and divide by the square root of 30, I can guarantee you would get this number right here. This number is the average distance that each individual is away from the mean, and this number is the average distance that each x bar, each sample of size 30 is away from the true mean, okay? Standard error of the mean. And then here's our test. We're running a difference in between mu and mu male and mu female. Here's our estimated difference. That's just going to be the difference between these two means. Don't worry about the confidence interval. A t-test for the difference. The null is that it equals 0 against the alternate that it's greater than 0. Test statistic, p-value, degrees of freedom. Okay. So on the AP test, you're probably not going to run it on your calculator. You're just going to look at computer output and pull the values from it. Kind of crazy, right? Like, not only do you not put it in, we talked about using the formula. Not only will you not put the data in your calculator and even run the program on your calculator, they're just going to give you the values So all they really care about is all this interpretation and how to say things right and check the conditions and all that crap. All right. Example 2. You are wondering so again, if I don't read the text, if I just look at this, I see I got a group of boys and I got a group of girls. I got 2 samples. Some people are just going to run a 2-sample test without even thinking about it. And they're going to lose a lot of points. We have to read and think about it. You're wondering if the male and a brother-sister twin pair are taller than the female twins. So we got twins, and we're wondering if the male twin is taller than the female twin. You randomly select, this is a typo, it should be 10. You randomly select 10 twin pairs and record the heights of both siblings. So this is linked data. This is a twin pair, a boy and a girl. I can't change the order. One list can't be longer than the other. This is a matched pairs design. So when I analyze this, I need to look at the differences and do a 1-sample test on the differences. So I shouldn't be looking at this graph. I shouldn't be looking at this test. The reason I gave you these values was to just illustrate that the power, actually I think I didn't comment on this, I'm sorry, on a previous video. I think I forgot to. Oh, no, I did comment, I'm sorry. Sorry, I'm not redoing this video though. The reason I put these values on here is so you can kind of see how a paired test is kind of more powerful. When I look at this data, it looks like the sisters are a little bit shorter than the brothers, like on average, right? A little bit. Like the guy's average is here and the girl's average is there. But it's a slight difference and there's so much variability. So how can we combat all that variability? Because that variability is working against us. In this test, if we do a 2-sample test, I do not have enough evidence. So my p-value is too big, I don't reject, and I'd say there's no difference. But this is the wrong procedure. We really shouldn't be looking at it at all. In fact, if some statisticians watching this are like, well, you can't even run it. You're right. You can't even run this at all. It's not an independent sample test. Or my samples aren't independent. What I should be doing is a matched pairs test. So here's the difference list. I'm looking at the differences and I'm wondering if the differences have an average that's more than 0. And it looks like we do. Looks like my average is quite a bit different than 0. So I have a more powerful test. I reduce the variability because here's a tall set of siblings and here's a short set of siblings, right? We're reducing that variability from sibling to sibling, family to family. So this test gives me a p-value of 0.01, and now I can reject the null, and I do detect a difference. So that's what kind of happens when you do a matched pairs test. You increase the power of the test. You increase the probability that you can detect a difference if in fact there really is a difference. Okay? And that's it. Good luck.